Number 1. How do you solve an absolute value equation? So to do that, we can use the definition of absolute value, which is the absolute value of, let's say, some number k will equal k itself if k is greater than or equal to 0, or negative k if k is less than 0. In other words, if k were a positive number, let's say 7, absolute value of 7 is k itself, 7, since 7 is greater than or equal to 0. If k were negative, like k was negative 7, then this would apply here. So the absolute value of negative 7 would be the negative of negative 7. K is negative 7, remember. So it would be positive 7, obviously, right? Using the definition. So let's suppose we have an absolute value equation. Absolute value of x is equal to k. This represents capital X, and I know it looks like Roman numeral 10, but we can also use that symbol to represent capital X, uppercase X. That could represent either a variable x, lowercase, or could represent an expression, an algebraic expression. So if you're taking the absolute value of some algebraic expression, you can symbolize it like this. All right, so this would cover a lot of territory in absolute value equation. So let's say you have absolute value of something equals k. Then by definition of absolute value, the expression inside the absolute value bars will equal k or negative k. Okay? So that's basically how you would solve an absolute value equation. Now what you would do is you would work with both of these, and OR here represents the union of the two solution sets. All right? So you would work with these two, solve them for whatever it is you're solving for, and then take the union of the two solution sets. All right? And that's what the OR represents. I have it written up here. All right, I have the three possible cases for absolute value equation and inequalities there as well, and that's how you would set up the solutions. All right. Now there's one instance. If k is less than 0, there is no solution. That symbol represents no solution, or the null set. All right. In other words, if absolute value of x equals, let's say, negative something, like negative 7, there's no solution, obviously, because the absolute value of something will never be negative, never equal some negative number. All right? So if you see something like that, for example, on a test, you would just put this symbol for no solution, or write no solution, or empty set, or however it is you want to do that. But there's no need to go any further with that, because your professor probably threw that in just to throw you off, all right? Or to see how you were thinking, let's put it that way, all right? Don't just mechanically go through all these with your little, you've got these things here to help you solve these, and you want to memorize those, but you don't want to turn off your thinking ability. You don't want to become a robot, all right? So that's why they'll throw in some of these questions like that to see if you're thinking. So if absolute value of x equals some negative number, you know there's no solution. And you would just write that down and move to the next question. Number 3. When solving an absolute value function, the isolated absolute value term is equal to a negative number. What does that tell you about the graph of the absolute value function? Well, the graph of the absolute value function does not cross the x-axis. So if you look at page 94, example 5, for instance, the function given there is g of x is 4 times the absolute value of x minus 2 plus 2. Alright? Now if it crosses the x-axis, then setting it equal to 0 is going to give us at least one solution. So let's do that. Alright? So move the 2 to the other side. Divide both sides by 4. That reduces to 1/2, negative 1/2 rather. So we have absolute value of x minus 2 equals negative 1/2. Alright, well obviously there's no solution. Absolute value of anything is not going to be less than 0. It's not going to be negative, like we just mentioned in the problem number 1. Alright, so there's no solution for this. Number 5, how do you solve an absolute value inequality algebraically? Alright, well there are two basic types of absolute value inequalities. Absolute value of some expression is less than or equal to some number, k, or absolute value of some expression is greater than or equal to some number k. Alright, there could be strict inequalities here without the equal part as well. You would just treat that in a similar way, except use the same symbol that was used in the original expression. Alright, so if it's this one, then you would write negative k is less than or equal to, or just less than, if that's what you have up here, the expression without the absolute value bars, and that's less than or equal to positive k. Okay, and you can think of this expression here, absolute value of x, whatever x is, can be written like this: x minus 0 in absolute value bars, right? So this would represent the distance between x and 0, and we're saying that it's less than or equal to this number k. So if you drew that on a number line, here's 0, alright? So the distance from x to 0 is going to be between negative k and k. That would be anything in here. Alright, x would lie somewhere in between these two. And that's what this is saying here. X is between negative k and k, right? Negative k and k. The distance from x to 0 is less than or equal to k. Alright, so that's, you can look at that graphically and see why you set it up that way. I'm sure your professor has probably covered this before, but that's a reminder for you. So you can solve it as written here pretty easily, alright? And you can also separate those like this. You can solve it just the way it's written, or you could separate them like this. Negative k is less than or equal to x, and don't use or there, and has a specific meaning. X is less than or equal to k. And then you solve those separately, and then you take the intersection That's what the and means. What do they have in common? That's what you're doing. What do the two solution sets have in common? That's what you would use, would be intersection. So that would give you the final answer. All right. So that's how you would set this thing up here, this part. Okay. But this way, doing it this way is a little bit more involved. It's easier just to keep it like this and solve it that way. You'll see some examples later. Now if you have this case here, if we look at this on a number line, think of that as being the distance from x to 0 is greater than or equal to k. So here's 0 on the number line, here's k, and here's negative k. So this distance represents k units, either left of 0 or right of 0. So that means that the solution is going to be out here either direction. All right. So x could be out here somewhere, so the distance between it and 0 would be greater than k if it were out here, let's say, or out here. All right. It would be equal to k if it were right on the dots there. Okay, so that's the geometric reasoning behind that. So you would set up these two inequalities. Just x without the absolute value bars is greater than or rather less than or equal to negative k. That's this part here. Or x is greater than or equal to k. Right? That would be this part here. All right. And or represents union. So you would take the union of those two solution sets when you solve each of these separately. Unfortunately, you can't write it all as a single expression and solve it nicely like you can in this case. All right, so you have to write them separately and solve those separately, and then take the union of the two solution sets. All right. Number 7. Describe all numbers x that are at a distance of 1/2 from the number -4. Express this using absolute value notation. Okay, so drawn on a number line, it looks like this. There's -4, and we want to go a distance of 1/2. Let's say that's 1/2. Units away. So this would be -3.5 right there. And here's another 1/2, let's say, right here. So that would be -4.5. All right. Okay. So to represent the distance x to any number k, you write it like this: absolute value of x minus k. That represents the distance from x to any number k. All right. So you would express this distance in absolute value bars as x minus -4. Absolute value of x minus -4. All right. That's the distance from x to -4. Now that can be simplified as, well, we're saying it's 1/2, all right? So set that equal to 1/2. So the distance from x to -4 is 1/2. Or you could write it like this, just simplify inside the absolute value bars. X plus 4, absolute value of that equals 1/2. All right. So that's how you represent the distance between x and -4 equaling 1/2. So, well, what is x then? What is x? You take this one, use this format right here. Absolute value of x equals k. Here, the capital X is x plus 4. K is 1/2. All right. So the expression equals negative k or k. All right, so x plus 4 equals negative k, that would be negative a half, or represents the union, x plus 4 equals positive k, right there. All right, and then you solve each of these separately. So if you add or subtract 4 from both sides, you get x equals negative 4.5. And here you would get, subtract 4 from both sides, negative 3.5. So you take the union of those two answers, so you get negative 3.5 or 4.5, negative 4.5. All right. Number 9. Find all function values f of x such that the distance from f of x to the value 8 is less than 0.03 units. Express this using absolute value notation. Alright, so the distance between f of x and 8 is represented by absolute value of f of x minus 8. And we're saying that this distance is less than 3/100ths. 0.03. So there's our inequality. Let's solve this. We can use this format right here in the middle. Alright, except we're using less than and not less than or equal to. Alright, so you've got negative 0.03. That's your k is 0.03 there, so that would be negative k. Is less than or equal to, and then the capital X represents the expression, so you put that whole expression in here, f of x minus 8, and that's less than positive k, or 0.03. And then you solve this, you add 8 to each of these. Oops, I should not have put less than or equal to. That was on my mind talking about that just now. Alright, let's erase that equal part there. Get this thing correct. There we go. Anyway, you would add 8 to each of these three expressions separated by the inequalities, and so you would get 7.97 is less than f of x. Add 8 to that and you get 0, so it's just f of x, and that's less than 8.03. So f of x has to be between 7.97 and 8.03 in order for that to be true. Number 11. For the following exercises, solve the equations below and express the answer using set notation. Okay, so we have absolute value of 6 minus x is equal to 5. Alright. So again, we use this setup here. 6 minus x is equal to 5, or 6 minus x equals negative 5, and solve each of these separately. So we can subtract, or you can move this, think of moving the negative x over to here, make that positive x, transpose the 5 to here, make that negative 5. So you're going to have x is equal to 6 minus 5, or 1. Alright? Here you can move or transpose the negative x to the other side, make that positive x, transpose negative 5 to this side, make that positive 5, so you get x equals 6 plus 5. or 11. So you take the union of the two because of the or there. So take the union of the two answers and you're going to get a set with the two answers, 1, 11. Number 13, absolute value of 4x minus 2 is equal to 11. So again, we have this first situation here. So we've got 4x minus 2 equals 11, or 4x minus 2 equals negative 11. Solve those separately. And so we've got adding 2 to both sides on this one. You've got 4x equals 13. Divide both sides by 4, you get x equals 13/4. And over here, you add 2 to both sides, you're going to get 4x equals negative 9. Divide both sides by 4, x equals negative 9/4. So the solution set is negative 9/4 and 13/4. Incidentally, you could approach it like this. Absolute value of 4x minus 2 is equal to, factor out the 2 out of these two terms, so you get absolute value of 2 times the quantity, 2x minus 1. Now this would be the situation where you have absolute value of a times b equals absolute value of a times absolute value of b. Remember that rule? So that would equal absolute value of 2 times absolute value of 2x minus 1. And then that would be just 2 times absolute value of 2x minus 1. And then you could divide both sides by 2 up here. So you'd get absolute value of 2x minus 1 equals 11/2, and then proceed from there. Although this one is already pretty simple, you don't really need to do that, but I just wanted to show you you could do that if you wanted to. It may be helpful in some situations, not really in this one, but in other situations you could do that. Number 15. So we have 3 times the absolute value of 5 minus x is equal to 5. By the way, before I solve this, I want to note something here. Absolute value of 5 minus x, let me go over here. This is separate from the problem. Can be written like this: the negative of x minus 5, right there in absolute value there. Right? Does that make sense? Negative times that is negative x. Negative times that is positive 5, so you get that. This is, think of that as a negative 1 there. So that's absolute value of negative 1 times absolute value of x minus 5. Absolute value of negative 1 is 1, so it's just absolute value of x minus 5. You could, instead of working with this, you could work with x minus 5 if you wish, because they're equal. In fact, why don't we do that? So, just to see what happens, right? Because we already know that these are equivalent, so why not? So divide both sides by 3. So you've got absolute value of x minus 5 is equal to 5/3. So that means x minus 5 equals 5/3, or x minus 5 equals negative 5/3. Alright? So add 5 to both sides. So you got x equals 5 plus 5/3. Now before I can add these, I need a common denominator, which would be 3. So multiply 5 by 1, but I'm going to make that 1 equal to 3/3. Alright, you're multiplying by 1 because you don't want to change the value of this. You do want to give it a common denominator, so you would multiply by 3/3. That will give you a denominator of 3 plus 5/3. So this is, think of that as 5 over 1 times 3/3, that's 15/3. Plus 5/3. Now that they have same denominators, we could just add the numerators. That's 15 plus 5 all over 3, which is 20/3. Over here, you add 5 to both sides. You've got x equals 5 minus 5/3. We already know that 5 is 15/3, so I'll just use that. 15/3 minus 5/3. They have the same denominator, so you can combine the numerators. 15 minus 5 all over 3, and that's 10/3. Alright. So we have two solutions, 10/3 and 20/3. So if you check the answer in your book, you'll see that it's exactly in agreement with the answer in the book. And so the point there being that you could, instead of using this, you can use this expression. All right. So I do think it makes it a little bit easier to solve because you don't have that negative x sticking in there that you have to deal with. All right. It's not a big deal, but it's a little something that'll make it a little quicker. Okay, 17. 5 times the absolute value of x minus 4, and then outside of that, minus 7 equals 2. 5 absolute value x minus 4 minus 7 equals 2. Alright. So first you add negative 7 to both sides. And you get 5 absolute value of x minus 4 equals 9. Alright. And then you divide both sides by 5. So you've got absolute value of x minus 4 equals 9/5. Alright. So x minus 4 equals 9/5, or x minus 4 equals negative 9/5. Alright. So add 4 to both sides. X equals 4 plus 9/5. Multiply the 4 by 5/5 to get a common denominator. And again, 5/5 equals 1, so 4 times 1 is still 4. That's very important. You don't want to change the value of that, but you do want a common denominator. And then plus 9/5. So 4 times 5 is 20, so you've got 20/5 plus 9/5. And that's equal to 20 plus 9 all over 5, or 29/5. Alright. And then over here, add 4 to both sides. 4 minus 9/5. So that's 20/5 minus 9/5. And that's 20 minus 9 all over common denominator 5. And that's equal to 11/5. So the solution set is 11/5 and 29/5. All